Our next speaker is Mr. Markus Moesenbacher. He is a system architect at Infineon Technologies, Austria. First, I will request Dr. Balaji R to felicitate our speaker. Sir, please. Mr. Markus is a renowned system architect with a wealth of expertise in the field of security device and identity solutions. With a strong background in product definition and portfolio management, Markus has developed a unique understanding of the complex interactions between hardware and software components in government identity solution, mobile identity applications, and payment system. Mr. Markus holds a master's degree in electrical engineering from the University Graz, Austria, and an MBA from the Californian Lutheran University, California. He has more than 20 years of experience in the smart card business in different positions.
For your introduction. Good afternoon to everybody of you. Thanks a lot for the invitation. It's an honor to talk about PQC, and I'm focusing on security controllers, which are also called secure elements, which are used in applications like IoT, in passports, payment networks, and also in a TPM, which was mentioned just before. So PQC first, maybe I start with quantum computers in general. So IBM has introduced the first quantum computer in 2019, the IBM Q System 1. And the main difference between classical computers and quantum computers is that classical computers are working with zeros and ones, and quantum computers are working with the superposition of 0 and 1. So you never know the result. It can be 0 or it can be 1. And you can also see it as a bit which is on the sphere, and it can have either 0 or 1. So quantum computers can solve problems which currently cannot be solved with classical computers. There are several applications, and we are focusing today on attacking asymmetric cryptography. So we will have, in some years from now, we will have a threat in security which we need to solve. So especially asymmetric algorithms are endangered, like RSA and ECC. So RSA is based on prime factorization. So this means it's a product of two prime numbers, and it's very hard for classical computers if the keys are long enough to get the two primes out of this product. So a classical computer needs about 100,000 years or longer. If we take a 2000 bit RSA key length, and the quantum computers just needs some minutes. Symmetric algorithms are not endangered. If you use AES 128, it's sufficient. However, countries like Europe and also in Europe propose to use 256 bit-sized AES keys. So if you take a look, we are not there yet with the quantum computers. In this graph, you can see the number of quantum computers. So there are always press releases about IBM and Google. We have already several thousand qubits. But it's not about the number of qubits, it's about the quality of qubits. So the challenge for the quantum computers is the error correction. So here you can see several providers of quantum computers. And you can see also here, for example, the Quantinuum, which is on the left-hand side. It doesn't have as many qubits as IBM, for example, but the quality is much higher. And we need to go to the left side into the green zone to be able to use the quantum computer for different applications. And at the top, you can see what is needed to crack a RSA 2048 key. So as I said, we are not there yet. So currently, quantum computers can provide 10 up to 40 high quality bits, so also called logical bits. And so only 0.3 to 1% of the capacity is available to be able to crack a RSA 2048. But with 4,000 logical qubits, it will be possible to crack also RSA 2048. Nobody knows when we are there, but it's expected that it will be between 2030 and 2035. So not a long way to go there. So this means we need to think now already about tomorrow. So we have different challenges, which were mentioned also before already. Harvest now to encrypt later. So you can harvest now valuable data, which is encrypted with RSA and DCC, and you can simply crack it then with a quantum computer. It's also about sensitive information, which is used for governmental person data or also for payment. And we also need to think about applications in the industry for aeronautic and also automotive and industry, which also was shown in the last presentation. So depending on the application, we have different challenges or different threats. So for mobile phone, possibly it's not that dangerous now because you have it usually up to 8 years. It's already a long time to use a mobile phone. Or for electronic document, it depends. For payment applications, credit cards, it's not so dangerous because they used 5 years. And ENVCO, which is the standardization organization for payment cards, even only thinks to introduce PQC secured devices in 2038 because they say the current security is sufficient with the current infrastructure. But for ID cards, it's different because a passport is 10 years in the field. And based on that, we need to be prepared already now to be PQC secured. Also for cars, automotive have a 15 years lifetime. Here it's even more important to take care about PQC as well as for industry applications which are used up to 30 years. So when is the Q day? So nobody knows, as I said. Yeah, it will be about 2035 based on the feedback of several quantum computer providers. So the solution for the are the PQC algorithms. And as I said, I focus on embedded security. So first is the use about quantum safe security encryption algorithms. They need to be able to implement it in hardware, which is also a challenge for security controllers because they have not, so they have limited memory. And the first standards have already been deployed by US NIST, but there are also local PQC standards, like in Germany, BSI also has introduced some standards. But I will now focus on the NIST standards, which are mostly used. So yeah, we have different challenges. So we have the infrastructure challenge, which is also a PKI system. We have much bigger keys, which has to be taken into account. We will have bigger certificates. It's quite complex and full transition will need time. Then quantum computers also evolve and they are not waiting until we have prepared our products. And it can come in 5 years or in 10 years. And the solution is to have a PQC-ready hardware, which means that it provides the performance, the memory which is required. So the hardware fully needs to be able to support PQC, even though the application standards are not available yet. So meaning, once all the standards are available, it has to be possible to upload and to do a secure upload of the application, which also is called as crypto agility. So even if there are new crypto algorithms, they shall also be able to be updated on the device, which is already in the field. So here we come to the NIST standards. What is the most optimal algorithm for key exchange to be used in embedded security controllers is MLChem, which is a lattice-based algorithm. Then we have the MLDSA. This is for signature generation, for digital signature. This is also lattice-based. So those two algorithms are the optimized algorithms for security controllers. SLH DSA, it has very small signature size, much smaller compared to ML DSA, but it has the disadvantage that the performance is up to 6 times slower compared to MLDSA, and FNDSA, also called Falcon, is also a digital signature algorithm, which has very big key sizes compared to MLDSA, up to 6 times higher. This is also a disadvantage. And HQSA could be an alternative to MLChem, but it has the big disadvantage that it has bigger cipher keys, and it needs up to 400 times more calculation time compared to MLChem. So all those algorithms beside MLChem and MLDSA are not really able to be used in security controllers. Then we also have stateful hash-based algorithms like XMSS and LMS, which also can be used to secure an OS, so to check the integrity of an OS. The disadvantage of XMSS is that you can not use it unlimited, so you can only do some signatures. So the challenges for security controller. So as we know, there are certificates available for security controllers like common criteria, EMVCO certificate, which is quite similar from the testing and from the attacks. So the industry has already experienced, and the test houses, about more than 20 years. So many attacks are available, and so it's no issue to test a product based on the security level. For post-quantum cryptography, it's different. First, we don't have any quantum computer which is able to attack the chip, and there are fundamentally different algorithms. So nobody has tested those algorithms yet. So only with proofs those algorithms have been tested, and also the protocols then in the applications will be tested. So the countermeasures also need to be developed and proven in the framework, and the test houses need to anticipate the attack techniques, as also the implementer has to anticipate an improvement on the security measures. So here we have the example of a challenge to implement PQC in a security controller, because the signature sizes are much bigger. So we are not talking about bits here, we're talking about kilobytes. So the biggest key size is 5 kilobytes, which is really a lot. So it's up to 80 times longer than conventional cryptography. So what is the solution now for secured embedded applications? So first, we start with the security controller hardware, so hardware security. It's very important to extend the memory. So first, the NVM memory, because for crypto agility, you also need to implement in-field update. You also need additional cryptography. You need to implement hybrid mode. So hybrid mode means the combination of conventional cryptography with PQC cryptography, not for the sake of backward compatibility, it's for the sake of security. And then what is not available yet are the implementation in the infrastructure, the application standards, like for ePassport ICAO 9303, or for other applications. The protocols are not defined yet, and also the OS also needs then to be adapted to support the application. The PQC algorithms are already available and released by NIST, and they can be implemented already now. So in a nutshell, RSA and ECC are used in many systems, especially in PKI systems, and there is no simple drop-in replacement of the algorithms. Standardization is still ongoing for additional standards like Falcon algorithm, for example. And however, we need to ship today the products which can support PQC in 5 to 10 years from now. They need to be prepared. So at least the hardware needs to be prepared. And also we need to implement hardware accelerators to have a comparable application performance as with current security controllers. So what is our stake, Infineon's stake in this topic? So we started already quite early, in 2017. We made a demo project on a available chip, commercially available chip, by implementing the algorithm New Hope for key exchange. It was a passport application. And since 2018, Infineon is actively involved in several funding projects with other companies of the industries, also with customers. And in 2021, we released the first product. It is a TPM, which is using XMSS for code integrity of the operating system. And Infineon also actively contributed in the standardization at NIST with Sphinx Plus, which is also called SLH-TSA. It's a hash-based algorithm. And finally, in December 2024, we succeeded to get the first certificate with CCEIL 6+ certification of a security controller supporting MLChem. So this is a security controller which is used for eSIM applications, so embedded SIM applications. So actually, we are very proud about that success because it's the world's first certified security controller. And we also did a press release with the German Federal Office for Information Security, BSI. So the challenge was here to implement the right security models, also the PQC acceleration, which we implemented in the hardware, and also the bigger memory. It was also a challenge for the test houses because they don't have that much experience with the attacks. They needed to anticipate the attacks which could occur. So what we are doing, so we are the first on the market which can provide a PQC coprocessor, including the algorithms in a crypto library. And we use and implement this crypto agility with the Infineon product. It's the name of the security controller, which supports Integrity Guard 32. Integrity Guard means that it checks the program flow. So we have two CPUs, and if one CPU has a different result, then it will be detected by the security system. And we also have we also have EDC, which is a big error correction frame in the NVM and also in the RSA. We are also partnering with customers in the industry. We are partnering also with universities, and our global team can support you. We have in every region, we have PQC experts, which also can support our customers for implementing PQC secured and PQC prepared products. So thanks a lot, and I hope that you have learned something about PQC. Are there any questions?
Hi. So, see, home automation is going to be the future. So it's going to happen. So
Sorry, it's hard
the
to.
home automation. Home automation.
Home automation.
Yeah.
Home automation is also a topic. So it's referred to
Yeah.
IoT.
Yeah. So so we have multiple devices which are connected when we say home automation. So there are some devices which are very low power. So how good is the coprocessor which you are mentioning for the devices which is having very low processing power? So you said like there is a hardware.
Sorry, it's really hard to understand you from me.
No, I say that there are devices in a home automation. Consider in a home, there are devices which is having very low processing power. So which are still connected in the network. So with respect to security, you said you have a coprocessor which can be embedded with any CPU. How good it works with a device which is having a very low processing power?
How it works with the device which is used in the home automation, you mean?
Yeah, which is having very low processing power. Consider a washing machine, a fridge, which may not be having a much higher processing power.
Yeah, so for home automation, there are several standards like Matter, for example, and all those standards will also have implemented or they will be available also for PQC. So in home automation, in every device, you can have, for example, a security controller, which secures the access to the net. Or it could also be done like it has been shown in the industry example, that you just secure your whole network at the gateway. And this possibly makes most of sense.
And from your slide, we have seen that 2030, the quantum computers can able to break all the silicon chips. But no country is coming forward and they say that we have achieved this. Practically, as of today, there's no papers available that we broken the encryption. But some countries are saying that we have broken the encryption. But nobody is announcing outside. And PQC, the Q day is today, or the 5 years gap is still exist, 2030.
Did you understand?
The PQC, what you told, the quantum day 2030, all the encryption, the quantum computer can able to break all the silicon encryption, silicon chips encryption. It is 2030 or 2025. Some threat nations are not revealing outside that they had a powerful quantum computer. Even they are building with qubits of many qubits. Thousands, 10,000 qubits, but no country is coming outside and saying that today we had a powerful computer in the world. Now and then everybody says that we had a powerful computer, we had a powerful quantum computer. And that 2020, today we are in 2025, and 2030, the quantum computer can break all the encryptions. That is revealing today, or the so many state actors are not revealing outside. So because you'll be dealing with many of the stakeholders, it is true, or still we had a 5 years timeline to achieve that?
Mhm. So can you summarize your question there? I didn't really understand you.
My question is, 2000, by 2030, quantum computers can able to break all encryptions. What we are rely on silicon chips today. As post quantum cryptography came into effect, does it going to take 2030, or before that it's going to break?
It's such an
I will respond. So actually, as Marcus was saying, Q day.
Yeah,
will
Q
take
day.
time.
Yes, Q day, Q day, Q day.
Q day will
Yes.
take time. And the breaking of any current encryption is not based on the PQC. It is based on the capability of the quantum computers, and that is yet to build. We don't have very powerful quantum computers. It will take time.
Exactly, yeah.
Yeah, it will
So
take
in fact,
time.
he said that it may come up to 2035 or even later.
Right.
And though SOAR algorithm says that it can factor in polynomial time, but till now we have seen the success of only a number of 21, which is a very small number. So
Yeah.
we'll
Yeah,
have to wait.
that is came outside through papers through IEEE, but some nation countries are building secretly the quantum computer, which they are not revealing to the world. That's where I'm trying to ask.
Yeah, however, we need to be prepared already now to have hardware which supports quantum computers so that we are prepared in 5 to 10 years from now to support PQC. So these products need to be able to work with PQC algorithms. They need to support the performance which is required, also the memory, and also in-field update. So this is crypto agility, which needs to be supported already now to be able to support PQC once the application standards are available and the quantum computers can crack the algorithms.
Okay.
Okay. Yeah. Thank you. So at Infineon, I just wanted to ask whether you are working on any pluggable module which I can plug in even older device
Yeah,
so that it becomes PQC enabled.
you can also plug in it in an older device. However, you need to think about the interface. In theory, you can plug it in, yes.
Okay. Because we are also trying to work on similar thing so that we have a pluggable module. It can encrypt, and the other end another pluggable module which can decrypt. So that nobody has to change their device. They has to.
This is possible, yes.
Okay. Thank you. So thank you.
Thank
Thanks
you.
a lot.
Thank you for having me.